record on this computer, and I was going to. Thank you for the reminder. So I think that if, as you guys are getting ready to finish up the lab or, working on it, you still have another week or so, or roughly, just consider I think a lot of it's self-explanatory, the introduction. So let me just go over that real quick. So the introduction should have some discussion of what a bomb calorimeter is, what it's used for, what are its limitations, and what I would recommend is, you could have, a picture out of the lab manual of it showing it. You can put that in the experimental. So if you choose to not have it in the introduction, then you should definitely show it in the experimental. But also in the introduction, you probably want to discuss the main theory behind a bomb calorimeter is the fact that you're heating water up. And by heating water up, you're using the fact that you have a very accurate specific heat of water, and you can heat that water, and the bomb itself does a very good job of measuring all the heat that goes into that water while not allowing any heat to escape from out to the outside world or any heat from the environment to enter. So what you're really getting is the pure heat that came just from the sample that you burned. And so the main equation for that, of course, is the energy equals mass times delta T. Mass times heat capacity times delta T. And so I would explain that as kind of the premise for it. You don't have to go through and present all the equations that are in there. I would include the equation, the higher heating value equals W times T corrected minus EL over the mass of the fuel, and then define each of those. So as far as the results go, any questions on that so far? So introduction, experimental, any questions on that? Okay, so the results section should contain the data, and I think in the description I had the two, there's the table that I'd like to see, and that can just be taken directly from the data table that I gave you, and that would include all the parameters and of each test, including mass of the fuel, the W value, and the length of the wire, etc. You don't need to include all of the data with the temperature versus time. If you did, that's fine. You should also have another table that shows the 5 tests, the higher 5 higher heating values. So it'd be sample 1 through 5 with one column. The other column would be higher heating values with the 5 values, and then you'd have combined columns for the rest because the numbers are going to be the same. It would be the average higher heating value, standard deviation, and then in that same table you can put the propagated uncertainty and the statistical uncertainty, and then the root sum square of those two to show your total uncertainty. So that's something that you should have in your results section. As far as discussion, one of the key points in the discussion is the comparison of the propagated uncertainty to the statistical uncertainty, and that being that the propagated uncertainty is a measure of the experimental accuracy and the experiment itself. And the statistical accuracy, uncertainty, is a measure of the number of samples and how close you are to what we consider the true value. And so you want to compare those two and determine which one is bigger. So for example, if your statistical uncertainty is big compared to your propagated uncertainty, then that suggests that taking more samples or measuring more samples would be a benefit. But if your propagated uncertainty is big compared to your statistical uncertainty, then taking more samples will, of course, reduce your statistical uncertainty, but it won't reduce the overall propagated uncertainty. So that will dominate the overall uncertainty, and so there's not a lot of advantage to adding that. And so that's a concept that's probably one of the most important takeaways here, because ultimately, if you guys are out there making the big bucks and designing experiments of your own, then after you do your analysis of them, and you determined that the experiment itself has all the error, and that even if you did 1,000 more samples, then you would not benefit. And I saw this firsthand when I was early in my career at a hard disk drive company, and we were looking at different types of bearings to spin the disks. And we looked at how were we going to evaluate the wear on these bearings. And the first suggestion from management was, well, let's just buy $500,000 worth of these drives. Even though we were a hard drive company, we still had to purchase them from our supplier in Japan, and we had to then test them. And so we asked the question is, do we really need that many? So we actually did an analysis and to determine how many of these drives do we really need to show what we have within the confines of our experiment. And it was probably about a third of what they originally proposed. So it saved quite a bit of money. But so these are the kinds of things that you'll be faced with as you those are things you'll be faced with as you work out there. So I think I saw a question one of you asked about propagated uncertainty. If you want to ask that, that's fine. But if you do have a bigger propagated uncertainty than your statistical uncertainty, then you fix that by refining the parameters of your experiment. Now, of course, that's beyond the scope of this lab. I don't expect you to redesign the PAR bomb calorimeter, but it is something that you can use as leverage to management to say, hey, the equipment I have isn't going to cut it. And this is the reason why. If you want better uncertainty, we're going to have to spend more money to get better equipment to cut down on these uncertainties that are inherent in our current design. So I think that's kind of the takeaway of this whole lab. I don't think you guys will be making Soylent Green bars in your careers, but I think understanding design of experiments, and we're just scratching the surface here. So the reality is that you'll learn 99% of what you need on your job, but at least hopefully this will be in the back of your head somewhere if it does come up. Okay, so that's the bomb lab. Do you guys have any questions about it so far? I've had individual groups meet with me. I think most of it's been explained, but any questions about it? Okay. Well, if you think of any in the next few minutes, by all means. Now, I didn't want to keep you long, but I do appreciate you coming. I wanted to also mention the next lab that's coming up. And so what I'm going to show you now is so here is, this is our lab for the last lab, the strain gauge lab. Now, normally, if we had a live lab, what you would be doing is we'd be taking strain gauges. We have strain gauges connected to a cantilevered beam, and we would be calibrating the strain gauge. And the way we would do that is we would hang a known mass off of the beam and measure the voltage that the strain gauge produced. And then we would do that from 0 to 2,000 grams. And then that would allow us to hang an unknown mass and use our calibration line that we created to determine what the mass of that unknown was. Since we don't have lab, I've given you this data, and what this represents, what you're seeing here is we measured each mass 4 times. And so you can see the values, the high and the low values and the nominal values. And this is what you'll use, the nominal values. But these are the voltages that we had. So you may ask, well, why is there a voltage at 0 grams? And that has to do with, that's the baseline of the strain gauge, the way it's designed. So your curve isn't going to go to 0, but you should get a nice linear curve with this at the bottom and going up to roughly 18.9 at the top. Okay, so you'll go ahead and you'll plot that, and you're going to plot mass versus voltage, which seems kind of weird. You'd think that you would plot voltage versus mass, and actually, if you plot it either way, it'll work. But I find that it's a little easier to see. Excuse me. It's a little easier to see the uncertainty lines when you plot it as mass versus voltage. So let me show you this other page. I'll come back to this, but I want to show you this. Here we go. Now, this is an excerpt out of Chapter 9, out of your course pack. This is also, this section has also been uploaded onto the strain gauge module on the Canvas. So I want to get, what I want to show you is this is kind of the curve you're going to be creating. You'll have, instead of pressure, you're going to have mass versus voltage, and you're going to plot your nominal data, and then you're going to have these uncertainty lines. Now, what you may find,
Professor, are we
Yes.
supposed to see it right now?
Oh, can you not see this? Can you not see it?
No, not right now.
You could see the other thing though, couldn't you?
Yes.
Yeah.
Yeah, the
Okay.
screen share just stopped.
Thank you for pointing that out. That's a senior moment on my part. Let me get it back to you guys. I'm rambling on about something you can't even see. All right, there you go. Now you can see it. All right, now we're cooking with gas. Good. Okay, so what this represents is this is pressure versus voltage, and this curve will be similar to what you guys will create. It'll be mass, only it'll be mass versus voltage. And what's nice about this curve is what you actually have are the upper and lower confidence limits actually on the curve. And so instead of having to have error bars, this tells the reader that your data has this confidence to 95, 98, whatever percentage you choose. And so we're going to stick with 95% confidence limits. But what you are going to find is when you plot the data, because the strain gauge is really accurate, is that the lines are almost going to be on top of one another, and it won't look as nicely dispersed as this. So to combat that, what you can do is you'll plot your normal plot that'll look like this, but you'll also plot a second plot, or where you say go from full scale 30 to 40 millivolts, and then full scale maybe 20 to 30. In this case, it'd be pressure, or you'll go full scale between say 100 and 200 grams. So what all you're doing is you're basically expanding the graph, and so you'll be able to see that focused in part. Now this is the actual data, and so on the other Excel sheet that you'll download that has the raw data, on the second tab, it has something at the top that has these highlights. So what these represent is, you can see obviously X and Y, and then YC. Now what is YC? So after you plot mass versus voltage, what you'll find is you'll do a best fit line, and you'll get an equation for that line. If you then take that equation for the line, whatever it is, and you plug in the X value into it, that's the Y value you're going to get. So that's what your YC is. So you have, say, Y equals 6.5 plus 4, and then you go back and you plug in the X value into that equation for each point, and that'll give you your YC. Okay, and then all Y minus YC is just your nominal Y value minus the YC value that you calculated through using the overall equation for the line. And then you have this Y minus YC squared, X minus X bar squared, well, that's just the average of X, and then that you're able to calculate U. Now, how do you do that? So this part I think is pretty straightforward. You can just do that all in Excel. Now U comes from this equation up here. And so what this equation represents is here's your YC at a certain X, and then your U value is this whole term over here, where you take the T from your T-test, you multiply it by this S sub YX, and then it's this 1 over n x minus. So this is all, stuff you can pull from it. So this term s sub yx, that is actually found with this equation here. So all of this can be just programmed in Excel to do. It's not really that difficult. And that's why it's it's just a 1 week lab. Everyone will do their own and just submit an Excel file. So there's no formal write-up. There's no memo that you need to do. It'll be similar to the resistor plots. I just want you to create the Excel file and then show me the plot that you created that looks like this, plus the magnified part. And of course, you'll have your data sheet in there, and you'll have this. It'll let me to see everything you've done. And then the last thing is you'll have two unknown masses, or I'm sorry, two unknown voltages, and you'll have to tell me what the masses are, the nominal masses. So you have the two pet guinea pigs of Thorncroft, and you have to tell me what the nominal weights are. All right.
Will we need uncertainties on those as well?
On what? On
like the masses that we plug in?
I'm sorry, on the what you plug in? I'm sorry, I missed that.
On the masses we plug in?
No, you don't. So are you talking about the masses of the unknown hamsters? Or of the
yeah.
Oh yeah. No, what you'll do is for those you'll use the voltages, and you can get the unknowns, the uncertainties through the curve. So what I would do is there's a couple ways to do it. For example, if this was my graph that I'm showing here and it was exactly at 50 millivolts, I would just follow that up to where it intersects your lower confidence limit. And then what does that read as mass? And then your nominal, and then your upper. And that'll allow you to get a rough estimate of it. Does that make sense? So your curve should tell you, and it should be a pretty tight value, as you'll see. It's not going to be a large spread, but you do want to get that. Does that make sense to everybody?
Yeah, that makes sense.
Okay, good. Yeah, it's not meant to be. I know you guys have been working hard on the bomb calorimeter. I know that I'm going to be impressed by what I read, so much so that everyone will get A's. But do this assignment. This is not due until the end of dead week, so just turn it in when you can, and I will grade it accordingly. Actually, most of my time will be spent on the bomb calorimeter lab, but grading that. So you guys have any more questions on anything? Well, hopefully this was a little bit of help. I just want to check in with the class, and thank you guys, the few of you that came. I just want to check in and see if there had any questions on anything and kind of go over this. And I will post this, what I recorded, for what it's worth. But if no one has any other questions, then I'll call it good.
Thank you.
All right. Thank you, guys. Thanks for coming in.
Thank you.
Thank you.
Okay. Have a good day.
You too.
Bye.
Bye.
Thank you.
You're welcome.